So today I will give this talk and we will share our past few years experience working on garbage collection in Julia. So this talk is not about performance, it's about software engineering on garbage collection in Julia. I will talk about the challenges we faced, the decisions we made, and the lessons we learned along the way. So this is a collaboration between the MMTK team, RelationalAI, and JuliaHub. RelationalAI is the sponsor of this work. They are one of the largest users of Julia in production. They build their core systems all in Julia, like the compilers, database engines, web services. So Julia is mostly known for its use in the field of scientific computation. So you can see the workload from RelationalAI is quite different. So this exactly motivates this work. So we need the need to rethink about garbage collection of Julia in the context of large-scale and memory-intensive systems. So this brings us to our first motivation. Julia's current garbage collection, which is a sticky mark-based collector, it performs well in certain domains, but it's suboptimal for memory-intensive workloads, particularly in terms of memory fragmentation. So what would be a solution to this? At first glance, it seems obvious. We just replace this GC with a better GC. But the question comes, what do we exactly mean by a better GC? So we see like some GCs are optimized for latency or pause time, throughput, or fragmentation, and some GCs are more concerned about the complexity of GC itself or its interoperability with native code. So this brings us to our second motivation of this work. So we see there's no silver bullet GC. So every GC is made with different trade-offs, and they target with different priorities. So we don't want to replace the current GC with another GC. Instead, we want to introduce an interface that enables Julia to support a wider range of GC algorithms depending on the needs of users' workload. So the goal for this work is we want to introduce a GC interface. We want to be able to run multiple GC implementations with Julia, and we want to enable more advanced support for Julia. For example, the copying GC, not that advanced. So before we dive into our experience, I'll give a little bit of background. So first, Julia is high-performance, dynamically typed languages. It's designed to be as easy to use as other dynamic-typed languages like Python, but while being able to deliver good performance like statically compiled languages. There's a bunch of interesting features about Julia. The only thing I want to mention here is its seamless integration with C. So calling C function from Julia is easy and efficient. It's so easy, so it becomes a pattern that the Julia users, they just wrap and reuse native libraries in their Julia program. So this is absolutely good for programmers, but it causes challenges for GC developers. So Julia's current GC, it implements a sticky mark-based collector. It's strictly non-moving. It has a generational behavior. In terms of allocation, use a free list allocator. For small object, this is also known as the pool allocator in Julia. For large object, it uses malloc. And for permanent object, use malloc or mmap. Also, Julia may have object in the system image, in the pre-compiled system image. So Julia uses post-red barrier to capture updates to mature object. This is common for generational GCs. And Julia GC is also precise. They use shadow stack to record all the roots, and the tracing starts from those roots. So MMTK is an open source framework for building garbage collection. It includes a various of different garbage collectors, also known as GC plans. So this talk is not about MMTK. We use MMTK mostly for two reasons. One is we're familiar with it, and it's convenient for us. And the second is this framework has a well-defined GC interface. It has been ported to different languages. So use this for us to experiment the GC interface for Julia is a good choice. So in the rest of the talk, I'll talk about two parts. One is about how we integrated non-moving GCs with Julia. And the second part is how do we support a moving GC in Julia. So for non-moving GCs, we selected a list of GCs and integrate them in the order of increasing complexity. So in this way, we only need to focus one piece at a time rather than getting overwhelmed by the complexity. So this approach turned out to be very effective. So we started with a very simple GC called no-GC. So it just only does allocation and no reclamation. So this allows us to explore the allocation interface for Julia. Once this is done, we worked on the first real alternative GC for Julia. That's Emix. Emix is marked region collector with optional opportunistic copying. So at this stage, we disable copying, still to make things simple and manageable. So this, in this part, we use Julia's own GC as a reference. So we implemented the root enumeration and object scanning for MTK GCs. And we also found that a large chunk of Julia's existing GC utilities can be reused, like the save points, weak references that finalizes. And once this is done, we move to a similar collector that's very similar to Julia's sticky mark sweep. We use a sticky Emix. We still use the non-moving variant here. So in this part, allows us to understand how red barrier works with Julia. So a general experience for this part of work is it was smooth. The reason is the alternative GCs is more or less like its existing GCs. So the runtime and the language design already have good support for this style of GCs. We also found some quirks along the way. For example, like buffer object, this is a special kind of object. They don't have any pointer information, so they cannot be scanned by the GC standalone. They have to be scanned along with the object that owns those buffers. I won't talk through about each topics. So if you are interested, you're welcome to take a look at the paper. This is a roadmap for what we have done. So you can see that the prototype for all those non-moving GCs is mostly done in 2023. And in the last year, we upstreamed the GC interface and we upstreamed the non-moving Emix. And we're also in the process of upstreaming the non-moving sticky Emix. So all this work is actively making its way to Julia's GC ecosystem. So let's talk about moving GCs. So as we said, that non-moving GC has a fundamental issue that will cause fragmentation in the long-running workloads. You saw that we have done the non-moving GC mostly in 2023. Now it's 2025. That's roughly how long it took us to move object in Julia. So why is this so hard? The reason is simple. There's a deep assumption about non-moving in the language runtime, in the compiler, in the language semantic, and also even in the user patterns. So let's look at one simple example. This is a snippet of Julia runtime code. There's nothing too special about this code. You can see this everywhere in Julia runtime. This pattern here is very common. So let's look at this. So from this code, we have a root pointer pointing to it's from outside the heap, pointing to a heap object. So this is a root. By definition, it's a root. And later, we'll have another root. So but what you can see is, for the first root, there's a JL GC push. So that identifies this root and put it to the shadow stack. So we would expect that for the second root, we should have another push as well. But the thing is, for Julia, they don't do that. Why? So if we look at this code again, there's one piece of key information that's missing. So there's a pointer between the first object and second object. So in this case, the first object, that EXPR object, is kept alive by a root. So that means the second object will always be kept alive. So we call the first kind of root a dominant root, because the object it points to appear as a dominant node in the object graph. And similarly, we'll call the second kind of root a dominated root. So if we only look at the object liveness, the dominated root seems unimportant because those objects are always kept alive. So under the assumption of a non-moving GC, Julia assumes that keeping an object alive is sufficient. So in that case, Julia does an optimization. So they omit the report of dominated roots. So that's why we don't see Julia push the second root to the shadow stack. But obviously, this only works if objects don't move. So what happens when we have a moving GC? The garbage collector comes, see the first object. It knows this is a root and possibly being used in the native code. So the garbage collector can keep this object in place. There's no problem. But when we see the next object, there's no information for GC to know is there anything special about this object. So GC thinks, okay, I can move it. So it moves the object. Then what happens is this, what should be a root pointer now become dangling. So we found this core assumption in Julia. That is, if an object is kept alive, then they assume all the pointers and all the references to this pointer to the object will remain valid. We observe that this shows up in several ways in Julia's runtime. For example, the example I just explained, they could use this information to skip identifying certain roots. And also inside their GC implementation, they can use this information to skip tracing certain roots or skip tracing certain fields, as long as they know the object that is referenced by the root or referenced by this field is kept alive. Also, this shows up in their FFI. So explicitly, Julia says that the users need to keep object alive. Then they can use it. They can store it in their native program with no issue. So the middle two things is about GC implementation, and it's relatively easy to fix. So I'll talk about the other two. So initially, we tried an idea, we call it transitive pinning. The idea is if we transitively ping an object, then the object will be kept alive, and all the reachable object will be kept alive and also be pinged in place. So in this way, we can make the GC to satisfy their assumption. That is, if an object is reachable, it will be kept in place. So we have an efficient implementation for this. We just do an initial tracing that keeps those transitively pinged object in place. Then we do the normal tracing that try to move the remaining object. We had this working, but the problem, it pings most object, as you could imagine. So clearly this is not ideal, but this is a still useful mechanism for FFI. So when you pass a pointer to FFI, to your native code, you can use transitive pinning that give you a conservative and safe way to use this object. So instead, we took a different approach. We tried to identify the missing roots based on their location. So we found that there are a few places those kind of missing roots could appear. The first is obvious on the stack and in the registers. So we use conservative stack scanning. So in our conservative stack scanning, it's a bit different. When we find any potential references, we don't use them as roots. We just use them to ping those objects. So in that case, the GC is still precise. And the second place that this kind of roots could appear is in JIT code. But fortunately, there are only 3 places in the compiler that they emit pointers. So for simplicity, we just ping those objects that gets emitted into the code. The third location is the runtime native heap and the global memory. So the runtime is written in C and C++. So they may have data structures that in the C++ heap that reference Julia objects. So we identify in total around 11 runtime types that may reference GC object, but they're not really traced by the GC. So although when we identify those places, we also ping those objects. So the last location is the FFI. We realized that the current FFI is insufficient. It just simply don't give GC enough information to do copying. So we propose a new FFI, and the key to the new FFI is that the user will have to notify GC before their use of the pointers, and they will have to keep GC notified during their use of the heap pointers. So for this part of work, we have an Emacs that working with transitive pinning in 2023. And in this build, few objects can move. And roughly 1 year later, we have Emacs that without transitive pinning. And in this build, most objects can be moved by the GC. And just in last month, we made a proposal for the Julia community about FFI. So as a summary, we introduced GC interface for Julia. Both MMTK GCs and Julia's existing GC works well under this interface. We found it relatively easy to introduce new GCs under Julia's current constraints, that is non-moving, non-generational, or generational with object read barriers. We also found it possible to use moving GCs with Julia, but the GC has to provide efficient pinning support, and we're still improving moving GC with Julia. That's all for this talk. Thank you.
Thank you for a great talk. It's great to have practitioners come and explain what they're doing. So, did you say anything about concurrency, or is Julia concurrent? Is the garbage collection concurrent?
It's not concurrent, but it has a sweeping phase that can be done concurrently. Basically, just tell the operating system to with M device to reclaim those memory. That's the only concurrent part. Otherwise, it's not concurrent.
Okay. Any questions? Yeah. There is a remote audience, so please say your name and the affiliation.
Hello, Jeremy Singer, Glasgow University. Thank you for your talk. This is a question about social engineering, I think. How easy was it to convince the Julia community to accept your changes and to get them upstreamed? I mean, were you viewed with suspicion or welcomed with open arms? Thank you.
This is an interesting question. So yes, we have seen some resistance. Like people really like their current GC. And actually it works well for certain domains, as I have said. But there are also needs that other people want a different GC that works better for their workload. So that's the reason we not want to replace what they have. We give them something more. So I think in that case, we see much less resistance.
Yeah, we have time for one more question.
Martin Maas, Google DeepMind. Really enjoyed the talk. Do you see ways how the work on doing this for Julia could make it easier to adopt these GCs in other languages? Like, is there things that can carry over directly or indirectly?
I think there are two parts. One is, as you see, we use the framework MMTK. And when we put this framework to more languages, we're more confident in its own interface. That's one thing. And the second is a lot of things we realized, we learned in this experience is there's assumption in there that maybe really no one really figure them out what the assumption is. The assumption is there, but no one realized that. And we learned it in hard way throughout a lot of debugging. And then we realized, oh, they just don't tell us the roots. That's quite a surprising thing, actually.
Okay, thank you very much.